One fairly accessible differential equation that's easy to see how it plays out in practice or imagine how it works in practice is Newton's law of cooling, or sometimes it's called the law of heating and cooling. The law is fairly straightforward. It says that things heat up or cool down at a rate, so we've got a derivative here, that is proportional to, so going back to our translating the sentences, we have equals at constant times, the difference between the temperature H and the temperature of its surroundings. So we've got S, that'll be usually a constant for our purposes, though of course it could vary, and the temperature of the object itself. And the idea when we're done here is that H of t is equal to a prediction of the object's temperature over time. And this is meant to describe any scenario. So imagine a cup of coffee. You take a cup of coffee, you pour it, and then gradually it cools down over time. That would be a graph of H of t that would show cooling effects. If you take something cold out of the fridge and put it on the counter, it would heat up over time. H of t would be the prediction under these assumptions about how quickly that heating would happen. In terms of a differential equation, though, this is a nice equation because it is actually separable. K and S are both constants, and we're able to isolate the t's from the rest of the h's. What we're going to do is bring the dt up. And again, the k here could go down, can stay where it is. We'll leave it up. We have 1 over s minus h dh on the left-hand side. So that separate and integrate step works the same way here as in other earlier examples. And then the key thing is to recognize that s is a constant, k is a constant. We only have h's on the left, no t's, and only t's on the right with no h's. We then proceed by integrating both sides. The right-hand side is the most straightforward, it just gives us kt plus a constant. The other side gives us ln of s minus h, and we have to be a bit careful. There's going to be a -1 there. That's going to come out from the negative h part. S is a constant, doesn't really have an effect on the integration step. Our next step is to isolate for h, so let's get rid of the -1 first. We'll have s minus h, but we'll have negative kt minus c, bring the -1 over. Then we can exponentiate both sides, take each one as a power to base e. The e and the ln cancel each other out, they're inverses. We end up with s minus h, e to the minus kt, and times e to the minus c. Then we do our creative new variable creation here. We don't really care what c is, we just need to have a multiplier here as a factor. And we're also going to take away the absolute values. So we're going to end up with e to the negative c with a plus or minus as needed when we take away these absolute values. And when we do that, we end up with s minus h equals a e to the minus kt. And last but not least, we can bring the h over the other side, or isolate it. We will end up with s minus a e to the minus kt. And that is the general solution for a heating and cooling problem. Now it's worth asking a couple of questions about this precisely because we have some intuition about what happens when we take hot and cold objects and put them in environments. So what happens to the temperature of the object as the time goes to infinity? So what we're imagining here is the solution graph, and that graph would be a function of t, where h is our value, and s is the environment temperature. So imagine this is 20 degrees, our regular room temperature, and if we take something out of the freezer and put it in a warm environment, our solution looked like s minus a e to the minus kt. If you look carefully at this, the only t is in the exponent. And this expression here, as t goes to infinity, this expression here is a negative exponential, and so it will approach 0 in the long run. Well, if that's the case, then h is going to approach S, the environment temperature. What's H? It's our object temperature. So in the long run, the temperature of any object is going to approach the temperature of its environment, and it's going to do so in an exponential decay type form. So what we would get is a target temperature of S, and we would approach, we'd never really touch, but in practice we get very, 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 very close to that value in a finite amount of time. So an object that's cold, that's put in the environment, will heat up towards the environment temperature. And if something was hotter than the environment, it will cool down and approach the environmental temperature as well. Notice that's something that we couldn't necessarily predict directly from the differential equation. That's something that we need the solution to really see clearly. In the long run, what happens over time, that's not a question we can ask because there's no time explicitly in our differential equation. It's only available in the solution or our prediction about what's going to occur based on the differential equation.